Welcome to my classes on fundamentals of electrical circuits. Today we discuss Wheatstone bridges, which forms a part of several types of network structures like with symmetry, with the star delta, with infinite ladder networks, AC networks, etc. And what is special about Wheatstone happens to be the fact that they lend themselves to a lot of applications with respect to measurements because of balance. And another important feature of Wheatstone bridges happens to be the fact that each bridge gives rise to a pair of terminals or several terminals, wherein between these terminals no currents flow, whatever be the elements that you connect across them. Which is equivalent to an open circuit. Okay, similar, but at the same time, currents do not flow because both the terminals are at the same potential. Which means that if the terminals are at the same potential, this is equivalent to a short circuit. So, in a Wheatstone bridge gives an example wherein an energized one gives rise to an open circuit and a short circuit simultaneously. But let us look at the theory further through this example. So in this example, we see that the circuit tells us that there are two terminals A and B across which the source is connected. It may be AC or DC, and there are four arms such that P by Q is equal to R by S, which is the same as equal to P by R is equal to Q by S, or PR equal to QS, where P, Q, R, S are circuit elements. They can also be sources on the AC or DC. And there is a pair of terminals C and D diametrically opposite to terminals A, B, which is the pair wherein through which no currents flow, and so it's simultaneously an open circuit and a short circuit. Though it's a open circuit and no current flowing through it, it's an open circuit or a short circuit. So let's go through the problem. Here we see the elements of a Wheatstone bridge, obviously, and let's read what is required. In the following figure, if R is raised from 10 to 20, immediately you start to compartmentalize that there are two situations. R is first 10 and then it is 20. Okay, and S is raised by 5 to balance condition in Wheatstone bridges, as is expected because balance gives rise to measurements. Okay, then find the initial value of S. So immediately what you write out is in your mind, okay, that 20 by 10. The second situation is put first because 20 by 10 gives you 2. So 20 by 10 gives rise to S plus 5 by S, or in other words, 2 minus 1 gives you, that is 1 gives you S by 5, or S is equal to 5, as is one of the answers as is shown. Okay, moving on to circuit number 2 as marked here. Here we again see that it's a perfect Wheatstone bridge with an AC source. Okay, so AC source tells us 20 angle 0, where 20 is an RMS value. Please remember that. Okay, this is always going to be an RMS value, and there are impedances given. Okay, so impedances is very important because if it's given in impedance, then P by Q is equal to R by S. Okay, so in terms of impedances, resistances and inductances. But if they are capacitances, please remember that the reciprocals need to be used because the impedance of a capacitance is inversely proportional to the capacitance. Okay, so we see that J40 by J40, that is on the left hand side, the inductances gives a ratio of 1, which is the same as equal to minus J20 by minus J20. So definitely there is a Wheatstone bridge, and so there is a resistor connected across that is the diametrically opposite terminals, that is A and C, and so no currents flow. So let's have a look at the problem, because this problem was taken from a 5-mark question where the detailed solution needs to be given. Okay, so it's different, and I is not marked. So whatever be the I, we can calculate. Predict the current I in whatever part of the circuit in response to a voltage of 20 angle 0. The impedance values are given in ohms. Use the Thevenin's theorem. Okay, so we won't use the Thevenin's theorem. We'll just use the Wheatstone bridge, wherein we see that the current through the resistor is 0. Okay, what about the other two currents? We have 20 angle 0 faces J40 plus J40, that is J80. So 20 divided by J80 gives you a lagging current of 1/4 ampere. Okay, similarly 20 divided by minus J20 and minus J20 together gives you a half ampere leading current. Okay, so together, as shown in the figure, together they add to a leading current of 1/4 ampere. The third point is the third question is a pure Wheatstone bridge. As can be seen, there's a 6-volt supply, and there are from terminal A two resistances laid out, and then they club together to hold on 2 kilo ohms, and then they diverge back. This is exactly the way in which the Wheatstone has to be identified. Okay, so it's a pure Wheatstone, and no current should flow through 2 kilo ohms, as is asked by the problem. The problem can be seen the current in the 2 kilo ohm resistor in the show. Okay, they are all given in kilo ohms, and when you are getting kilo, please remember that you can leave them as such, and ultimately you can discuss in terms of milliamps or something like that based on whether they occur on the denominator or numerator. Okay, the fourth problem, again here we have to identify the Wheatstone bridge. A pair of terminals AB holds the source, and from A 1 ohm and 1 ohm diverge out to C and B, and then from C and D they converge back to B, and there's a redundant 2 ohms through which no current I flows. Okay, so let's see the current in the 2 ohm resistor is I. That's what it's asked. Okay, so moving on to the fifth problem, which is also again all these problems are gate problems. Here again we have 2 sin 100t energizing or powering the circuit, where 2 is the maximum value. So 20 angle 0 was different, it was RMS. This is 2 sin 100t, where 2 is the maximum value, and omega is whatever that occurs with t. Okay, in any sinusoidal waveform. Okay, so omega is 100. Okay, if it is required. Okay, now we look at terminal A, which is now not a point but stretched out to form a line. Okay, similarly for B, and C and D hold the component which may or may not have currents. Okay, so just let us look at the ratio of 1/1, which is the same as equal to two elements, that is a resistor of 1 ohm and the capacitance of 0.5 ohm in AD as also in DB. They are all the same. So we see that that no current flows through the 1 farad capacitor. So that's what is asked. Though currents do flow through the 2 ohm and 1 Henry circuit that is connected between A and B. So since only the capacitance is asked, we realize that the current is equal to 0. Now we come to a sixth problem, wherein we have again as said before, a single terminal A stretched out to form the top line of the circuit. Okay, similarly for B. Okay, and then if you look from the center towards the outward, you'll identify 3 different Wheatstone bridges. Okay, so or in other words, all the central elements of resistance R can be either replaced by a short circuit or an open circuit. It's all the same. Okay, so now let's read the problem. In the network shown in the figure, all resistors are identical with R is equal to 300 ohm. So each of these resistors is equal to 300 ohm. The resistance are AB, okay, which is the terminal resistance across AB in the network is. Okay, very simple. So you can short circuit them all. So you see that there is a network of 6 300 ohms in parallel, again in series with another 6 300 ohms in parallel. So it is 50 plus 50 100 ohms. Very simply, just without even just looking at the circuit, you can solve it. Okay, so moving on to the seventh problem. We see a lamp being lighted by a 220 volt DC source, and it leads to a Wheatstone bridge, perhaps, okay, depending upon the resistances, wherein CD happens to be a terminal which can be an open circuit or a short circuit. So the switching of the circuit does not matter at all. So what does it tell you? The resistances in the circuit of figure are of R ohm each. The circuit is initially open. What happens to the lamps when the circuit is closed? Okay, absolutely nothing happens, because it was an open circuit and a short circuit, and it went on to be physically a short circuit. Okay, earlier it was virtually a short circuit, now it's physically a short circuit, so nothing happens. Moving on to the eighth problem. Here we see a triangular structure, but you can see the Wheatstone bridge if you follow the terminals. Okay, so go from A, move on to C and D through a divergence of R resistances, and then from C and D go back to B, and you see that the same R resistance are involved. So there's a Wheatstone bridge making the resistance R connected between C and D redundant. Okay, and that's exactly what is asked. Find the equivalent resistance of the circuit across AB. So we see first encounter the short circuited or parallel to R. So it is R by 2 in series with the next pair. So R by 2 plus R by 2 is equal to R. Okay, very simple. Okay. The ninth problem is again looks like a Wheatstone. Let's see in the bridge. So of course we see 35 kilo ohms and 105 kilo ohms on the left side, energized by V sine omega t, and then on the right side we see capacitances. Remember, it has to be the reciprocals which need to be equated. Okay, and so now let's see. It's C1 and 0.1 microfarad. As I said before, the micro can be retained and ultimately used. Let's see what's the question. In the bridge circuit shown, the capacitors are loss free. Very important. And only in gate questions I noticed that this important aspect is mentioned. Otherwise, it will have to be capacitance plus a particular resistance, which will be indicative of the loss. Okay. At balance, the value of capacitance in microfarads. So you just need to calculate and then write out the answer in microfarads. You need not talk about you need look at the numerical values alone. Okay, so we have 35 by 105 kilo ohms. So 35 by 105 or 105 by 35, which is better because then you can write it as equal to C1 by 0.1 microfarad. Okay, so 105 by 35, immediately a feel for numbers tells you it's equal to 3, and 0.1 by C1 gives you C1 as equal to 0.1 into 3 or 0.3 microfarad. So now we go to the 10th problem. Okay, so Wheatstone bridge is obvious, but we have to find out Rx is very clear there, and it's powered by a DC source. Okay, so let's see. So we see R2, R3 multiplied by R1 directly. Let's see what the problem is. Okay, the answers tell us that all the values are different, so only one quantity needs to be calculated, the other will automatically come through. This is gate examination. Okay, when the Wheatstone bridge shown in the figure is used to find the values of resistor Rs, as we guessed, the galvanometer G indicates zero current when R1 equal to 50, R2 is equal to 65. So that's a good ratio, R2 by R1, 65 by 50, which is 13 by 10, and R3 is equal to 100 ohms. Okay, if R3 is known with 5% tolerance, which means that there are two values, an upper value as given by 105 and a lower value as given by 95. Okay, on its nominal value of 100 ohms, what is the range of Rx, which is exactly what we are able to find out. We see that Rx is equal to R2, R3 divided by R1, of which 13 by 10 is already ready, multiplied by 105. Okay, so because it's easier, because 13 into 105 gives you 1365 divided by 10, 136.5. That's answer A. Answer and the other part of the answer is easily obtained as 13 by 10 into 95. Okay, so moving on to problem 11, which looks complex, but it is very simple, and it's a little different in the sense that in the bridge powered by a DC source, we see that left side has PR identical, but the right side is giving a difference with a change in the upper resistance as given by R into 1 plus X. The lower resistance is pure R. Okay, so what is required? Okay, unbalanced DC Wheatstone bridge. This is the difference. It is unbalanced because of X. Okay, the Wheatstone bridge is shown in the figure. At what value of P will the magnitude of V0 be maximum? So P values are given, but what is important for us is X, not P, because X is bringing about the difference. Okay, X is bringing about the change in current and a difference in voltage. Okay, so we need to find out X, and then we can. Okay, and larger the value of X, larger is going to be the differential of voltage, and so a maximum value for V0 is going to come through as a result of this. So let's try to find out from the answers the value of P, and okay, that's the way it goes. So when X occurs on the denominator, or if it is minus X, you discard them. So C and D are discarded, and so A and B gives rise to X is equal to P square minus 1 for A, and X is equal to P minus 1. Obviously you choose answer A. The others are also given, but they are irrelevant. Okay, 12th problem, Wheatstone bridge is shown, again a variable resistance, and it's written as RS. Okay, powered by VI. Okay, so the VI is not yet computed. Okay, so let's go straight a strain gauge forms one arm of the bridge. Okay, very important. So strain gauges are important applications of Wheatstone bridges, wherein as the strain increases or the stress on the component increases, mechanical structures increase, we have what is called as the resistance increasing. Okay, and the figure below, and has a nominal resistance without any load. Okay, this is important. This is the basic minimum load. Okay, which is R. RS is equal to 300 ohms. Other bridge resistances are as is very clear. R1 equal to R2 equal to R3 is equal to 300 ohms. They should be equal. The maximum permissible current through the strain gauge is 20 milliamps. So it is sensitive, and it can allow only 20 milliamps. And as the resistance increases, the current decreases. So we have the maximum value, and so we have also the maximum voltage as given by 20 milliamps into 300 plus 300, two resistances in series, which is 6 volts. That's how you get the maximum voltage is 6 volt. Okay. During certain measurements, when the bridge is excited by maximum permissible voltage and the strain gauge resistance is increased by, so it's loaded, okay, and it increases by 1%. So the resistance goes to 303 ohms. Okay, over the nominal value, the output voltage V0 in millivolts is, okay. So the output voltage is created by the 3 ohms, that additional that has come into the picture. So and the right hand side remains the same because the powering voltage remains the same, but the left hand side current changes to 6 volt divided by 303 plus 300, which is 603, multiplied by the small resistance, the small change in resistance, 3 ohms. Okay, so it's near around 30 milliamps, and of the 4 answers you pick out the one nearest to 30 milliamps, which is okay. You don't need to calculate. Okay, from the understanding that 6 by 603 into 3 is almost equals to 300 milliamps. Okay, for the 13th problem, we have a complex structure, but it's very simple because we have resistance and reactive components wherein they can be equated separately. Okay, so what is okay, and we see that on the right hand side we have a parallel structure of a resistance and a capacitance, which is even better. Why? Because we should know that the R2 into R3 divided by R4 will give you R, and R2 into R3 divided by 1 by omega C4 will give you omega L. Okay, so let's see what the problem is. The Maxwell's bridge shown, okay, powered by AC circuit, so it's a Maxwell's bridge shown in the figure is at balance. Okay, the parameters of the inductive coil are, as was mentioned before, you can calculate R as equal to R2 R3 divided by R4. Okay, so very simple, and it's only one of the two answers. Of the 4 answers and the subsections of the answers, there's only one answer which corresponds. So you can choose it directly, but let us try to find out L also from the same understanding that it is equal to R2 R3 divided by 1 by omega. Okay, omega and omega cancel, so C4. So that it's going to be R2 R3 C4. Okay, so there's no doubt at all with respect to the answers. Okay, moving on to the 14th problem. It looks like a Wheatstone. It is not. Okay, so let's see why it is so. Because the left hand side gives you 1j by 1 by j, which is equal to minus j square plus minus 1. Okay, and on the left hand side you are having on the numerator. Okay, on the right hand side there is 1 by j by j, which is equal to 1 by minus square minus which is equal to 1 by j square on the denominator. So it's going to be minus 1 on the denominator, which is mathematically equal but electrically not. So okay, so be careful. But at the same time, let's see what it is. So we are given a source and a resistance, okay, which is facing it. Okay, the reading of the voltmeter in RMS value. So what is given is a maximum value. So division by root 2 for the circuit shown in the figure is, okay. So we have, let's say, let's look at the left side of the bridge. It is 1j and in series with 1 by j, because the voltmeter is almost equal to an open circuit. So that's equal to a 0 impedance, and the right side is also 1 by j plus j, which is equal to minus j plus j, which is again 0. So we have two short circuited paths and a 0.5 ohm resistor facing 100 volts. So it's 200 amps divided into 2, and so we have 100 into j. Or in the left side element, and on the right side element of the voltmeter we have another 100 by j or minus 100 j. Okay, and the voltmeter measures the voltage, which is the difference between the two. So it is 100 minus 100, so it's going to be 200 volts, but maximum value, so divided by root 2, it's going to be 141.4. Okay, very simple. Okay, the next problem, 15th one, we are not given the structure, but it is mentioned as a balanced Wheatstone bridge ABCD. Okay, so so obviously RCD equal to RDA into RBC, okay, divided by RAB. That is, on the numerator we will have components which have either D or C. Okay, so RDA into RBC divided by RAB. Okay, and what are the components? RAB is 1 kilo ohm with a tolerance. RBC 100 with tolerance. RCD is unknown, as was mentioned, as was spoken of recently, and RD is 300 with the tolerance. The value of RCD and its accuracy. So we can find out the value first and then its accuracy. Okay, so substituting, we see that 300 into 100 divided by 1 kilo gives you 30 ohms. Okay, so answer C and D are rejected, and of the two, the first answer is 30 plus 3 ohms, which means 10% tolerance. Obviously, it is not acceptable because you can't have such huge tolerance values. Okay, the second one seems to be more acceptable. Let's see the values. How do you calculate it? With the tolerance, the RDA becomes 301.2 and RBC becomes 100.55. They are the larger values, and on the numerator, on the denominator, you give the smaller possible value, which is going to be 1 kilo ohms minus 2.1 percentage of it. Okay, so which is 979. So and that gives you 0.9. This for confirmation sake. The last problem, that is the 16th one. It looks complex, but it is very simple, and that's the reason why I have marked out the capacitive reactance R as R minus JY, and the inductive reactance R as R plus JX, because the resistance values are the same, which is equal to 300 ohms. The other arm is 300 ohms, and there's an unknown impedance Z powered by an oscillator. Okay, so let's read. The AC bridge shown in the figure is used to measure the impedance Z. If the bridge is balanced for oscillator frequency, F is equal to 2 kilohertz. So that gives rise to 2 pi F, which is 2 kilohertz. Okay, and then the impedance Z will be. Okay, so first let us look at the answers. We see that for the resistive component, it's either 260 or 0. So you don't compute. You just chuck out 0 if it is not applicable. Otherwise, you use 0. Okay, and the others are all either 200 or 0 with a positive or a negative value. So there are two things to do. First, of course, we calculate the resistive components. What is the resistive component? It's going to be R plus Jx into R minus Jy divided by 500, which is equal to R. The active components will be R square plus xy, because minus J into plus J becomes plus R square plus xy divided by 500. So obviously it's not 0. So we chuck out B. Okay, so then we move on to the other component, which is going to be R plus, that is, you are going to have RJX minus RJY divided by 500. Only the reactive components. Okay, so we have you can take out 300, you can take out J, so it's going to be essentially X minus Y. Okay, so X has been written down here, 15.991, almost equal to 16, multiplied by 10 raised to minus 3 milli, then 2 pi, 2 into almost 3 into 2 into 10 raised to 3. Okay, so with all these approximations, it is almost equal to 200. You need not compute. Okay, similarly, y is 10 raised to minus 6 becomes 10 raised to 6 on the numerator, and it is 0.398. The capacitance value is almost 0.4, and then you have 2 pi, 2 into 3, and 2 and 10 raised to 3 for the kilohertz, 2 kilohertz. Okay, so that's almost equal to 200. So which means that X minus Y becomes equal to 0, and you choose the correct answer as 260 minus 260 plus or minus J 0. Okay, these are the other bridges. And there are other applications as well. As I said earlier, this finds the Wheatstone principle finds a hell of a lot of applications in several measurement areas, and even mechanical quantities. So the principle is very good. The principle also gives rise to a very interesting situation wherein a pair of terminals can be an open circuit or short circuit, as you choose. Okay, and as is more useful for you. Okay, another important takeaway from this class is that you can definitely use all kinds of approximations which will be useful for you. Okay, and the second takeaway is that you can multiply the branches across and divide by the branch, the component in the branch beneath across the unknown quantity. Okay, therein the real quantities can be equated, and the imaginary quantities can be equated separately, and you can find the solutions easily. Okay, another takeaway from this class is that, okay, I suppose I talked about the approximations. Use them use them as much as is possible, and you can arrive at the solutions. Okay. Another takeaway is that whenever you are having a variation, the numerator should have the larger values and the denominator should have the lower values for going for the largest variation possible, okay, for getting tolerances, etc. And also the fact that when you are having a differential voltage, the voltage is maximized by the change that is occurring in the system, and the change can be maximized only if you have at least one resistance behaving in a with a larger resistance value. Okay, so as I'm trying to remind you of the larger value for x that is required for getting a larger differential value. Okay, I suppose the remaining classes will also be interesting to you. Thank you.